Ready? And don't get scared. That was the computer talking. But introduce yourself. This is Fairport High School in Fairport, New York. And they're doing the ejecting robot.
Let's just go down the line. All right. I'm Emerson. And yeah.
I am Quinn.
I'm Gavin.
And I'm TJ.
Well, thank you for working on this. And if you want to share your screen or show us your prototype, I see it sitting right there.
We would like to show you our prototype.
Awesome.
So let's show our outer wheels first.
So we have two outer shells for the robot, which are both functioning as wheels and protection from the environment.
Nice.
And we have two inner shells, one of which has a hole for a camera, and the other of which has two pins so to hold it to the other one.
To me, it's amazing that all day we've been watching this, Dave and I and Nancy some, and everybody comes up with something completely different, which is really cool.
So this is just a model of the box with the dimensions. This is just the first one. So the ball will fit on the inside, and it has this sort of hinge. And this is going to be a part that's going to kind of protect the ball. So when it's up, it'll flip inside, and it will hold the ball. So when the sphere or robot won't move while the rocket is going. And yeah. So we're going to move to.
That's nice. That's a protection for the robot. Keep it in as secure while it's traveling to the moon. Good thinking.
Go ahead and share your screen. Okay. Let's find the right.
Can you see the presentation?
Yep.
Okay, good.
All right.
Good.
So we are using a Raspberry Pi processor as the core for our robot. It has more than enough capability to run anything we need to. We can connect motors to it, and it has a camera module.
So for the calculations of the force required for ejection, so we calculated roughly about 3 newtons required for launching the robot the 2 to 3 feet, or 2 to 3 feet for moon gravity, and something less than 20 newtons for Earth gravity. We need to do more testing to get the exact amount of force with also calculating the coefficients of friction. And the ideas for applying this force is tilting the box, but through our research, we figured out that tilting the box, an angle wouldn't work to have the sphere go that 2 to 3 feet. So we moved on to the idea of using pressurized air with a false back. So then the false back would shoot out and push the robot out along with it. And for the model and for testing, we got the idea of using a t-shirt cannon to get that pressurized air.
What's a t-shirt cannon?
It is So it's mainly used in like baseball stadiums where they put a shirt in a sort of like cannon and just launch it out. It has a air compressor thing attached to it where you could build up air, then launch the t-shirt out.
I've seen people throw T-shirts at games and stuff to the audience, but I haven't seen a T-shirt cannon. That's pretty cool.
Yeah.
Thank you.
This slide is just calculations, and it's just calculations, and this is just proof of work.
So for our robot, which we named Larry, we had to be able to power it and the Raspberry Pi itself. So the motor didn't really have that much of a requirement. We just needed it powered. So we decided on a 9-volt battery just to cut down on weight and size. And then for the Raspberry Pi, it requires a very specific power voltage in order to operate, which is between 4.75 volts and 5.25 volts. So they made a 5-volt battery, which would power the Raspberry Pi sufficiently.
So this is the full 3D model of our robot design. The 2 outer shells are made to fit together and enclose the inner shell. They are shown separated here so we can view the inner shell, which will also slot together with the assistance of the built-in pins. This is the outer sphere and the inner sphere.
So we know that our design is not perfect, and we have a few ideas on how to possibly improve it. A lot of those ideas have to do with our ridge design. They're meant to provide traction, and we want to know what the optimal number and size of the ridges are. We also want to know if the ridges should be offset or parallel. We also believe that we know what we want to do to protect the camera. As far as I know, we are planning on using a scratch-resistant lens, though we are also looking into using a lens cover. And of course, we always want to we can't rule out the possibility of changing our design to make it simpler or smaller, though we believe that we have landed on our final design. Well, final prototype. Final idea, rather.
So for our ejection system, as Emerson stated before, we are not going to use tilting anymore, which means that we have to have it propelled in a different way. So we decided on ideas in order to get the ball to travel faster without landing in the sand yet, because I feel the sand would stop all momentum the ball or Larry has. So we decided on ideas that include extending the distance it has to travel on a flat surface, such as this drawer idea, which comes off of the hinge idea we have, which would extend a small drawer-like platform out another 5 extra inches in order to make it travel further without going into the sand. Another idea we had was a cylinder or a guider idea, which, as Emerson stated before, would protect the ball while it is inside and also give it some extra distance to travel and guide it forward so it doesn't fall off track while exiting.
This is a sample of the code we will use to run the robot. We are using packages from the Raspberry Pi database for the motors and for the camera module. The sample on the screen should make the robot go forward, turn around, and take a picture.
That concludes our presentation.
Do you have any questions?
So I was just writing down some information about you. So you know how you have that protection thing? Hold that protection thing. Get that protection thing. So now you realize that you don't have to make that robot go 2 or 3 feet further when it jumps out of it, okay? Let me just make sure, Dave, is that correct? It just has to not drop underneath the the platform that shoots off the robot?
Correct. So for the demonstration at the CDR, your target zone is basically going to be about a 3-foot diameter plastic wading pool filled with sand, a couple of inches of sand. So you don't need to apply a whole lot of force to push this out. What if it clears the box, it's gonna arc down and come in, right? So you can kind of minimize the amount of force you actually have to do. I want to comment though. I'm impressed by the fact that you're already thinking about protecting the robot in the box while it's on the rocket. I advise all of the teams I'm working with, launching things to space, there's a lot of vibration. And one of the simple tests you should be able to do with your robot in the box is just rattle it like a Christmas package, right? And if you feel it bouncing around in there, it needs some more padding, right? It needs something to kind of restrict it. The question that I'm interested in, I'm really, your design is cool. What is actually driving that outer shell to impart mobility?
We are going to have 2 motors set within the inner shell connected by pins and axles to the outer shell.
Okay, so, and I saw on the inner shell, you had a spot where you intend to mount the camera, but you'll also have a couple of other spots where essentially you'll have something like an axle or something that can connect to that outer one. Okay, that makes perfect good sense to me. I like that design a lot. I really do.
So basically, Dave, so what you're saying is the inner diameter robot is how they're gonna control the outer part that's moving. Okay.
Yeah.
And yeah, okay, that makes sense. I was gonna ask a similar question.
Yeah.
Okay.
So what
So-
I was, actually, Dave, I want you to go. I can always
Well,
make my.
so guys, the shells that you printed, what did you manufacture that from?
It's PLA.
PLA. Okay. So I made the suggestion to some other teams this morning. Since you already have those shells printed and you know what the mass of the other parts are going to be, you've obviously got some motors that you've identified, the mass of your Raspberry Pi, etc. What I would do is put an equivalent amount of mass, secure it to the inside of that, and start dropping that thing, right? And you need to do it a lot, right? And the reason that I'm suggesting not start off with all of your components inside is simply the fact that you might end up cracking one of these. And you don't want to spend money on electronics and then have to replace it. But I would start doing some drop testing as soon as you possibly can, just so that you're convinced that you have the right thickness on that plastic, that it's going to hold up to that 6-foot drop. Okay?
All right.
Absolutely. Now, are the ridges going to go all the way around the ball?
Yes.
Okay.
So,
So effectively, it's really not going to matter what orientation this thing lands in, right? You're going to be able to get this thing moving, and I like that. That's a pretty cool design. Whose idea was that?
I'm not
second
actually
question.
sure.
Uh,
I'm not
it
actually
was
sure.
Emerson's for
For the what?
So I guess
Who came up with the sphere?
yeah,
Well, I
that was
mean,
Emerson. Yeah,
I
that
came
was
up with the idea of like that's
Yeah.
outer sphere and having like it be separate, so it could turn like it just has to.
Yeah,
Show it.
like take tank.
Yeah, it's like a
Motion.
tank. And it just, one side turns one way, one side turns the other, and that's how it rotates. And yeah, it's just simple idea.
And then I just came up with the part that there would be an inner
So
ball surrounded by it.
will that outer shell expand at all? Is it going to separate so that your camera has a clear view
Yes.
through it?
Yeah.
Okay. All right. So you also have to have some mechanism that's going to cause this thing to open out. What are your thoughts on how you want to accomplish that?
We don't really have any ideas for that at the moment, but we are working on.
Okay,
something.
fair enough.
Yeah.
That's a good answer. All right, very nice, guys. I'm impressed.
So what I was thinking about releasing the robot. All right. So you pretend this is that round thing that protects it. Pretend, do you see what I have in my hand? Yeah. So pretend that's there. And it's, instead of having it standing straight up inside, if you could put it on a little bit of an angle inside that box, so that when you open the door, this thing falls down and your robot just comes out of it. And maybe it would, do you see what I'm trying to simplify your ejection system, because they were thinking it had to eject 2 to 3 feet, but it doesn't now. So I like that you have that cover right there on your table there. And maybe it could be angled some way so that when you open your door, this slot goes so that it will just shoot the robot out. I don't know, but this is just a suggestion. So I know you have that one system, but I would make it simpler if you can, and more fail-safe.
Here's a simplistic thought, guys. If like, imagine that my hand represents the bottom of your box. If you put like just a slight slope on that, you've got a spear. It's going to roll.
Yeah.
It'll roll right out of there. And depending upon
That's
how
right.
much of an angle you impart, that will determine how much trajectory you're going to get on this. You may have enough space inside that box that all you really need to do is
Put it on
have
the
this
angle.
thing kind of tilted up a little bit. And as soon as your door opens, it's going to drop. Now,
Right.
we can always come up, people will say, well, yeah, what's that going to be in 1/6 Earth gravity when you're on the moon? Look, you don't have to worry about that right now.
Yes.
You're building this to test it here on Earth. And because of the fact that you have a ball,
Yeah.
it's going to roll. I mean, you could use simple, mechanical advantage and just let it roll right out of the box.
Yeah. From that, and I like your protection. So use your protection, but put it on an angle so that your robot is going to roll right down, and that's good. And call it good. Does that make sense?
Yeah.
Awesome. All right. Do you
guys
have
have
any
anything else to
questions for
share?
us? Or questions?
I actually do have questions. So, when the lander is coming down to the moon, do we have to account for the velocity the lander is coming down to the moon?
No.
Or,
Short answer, no. Now, in reality, in a real setting, yes, that's going to be a case. I mean, you're going to have thrusters that are going to be throwing up a lot of stuff, right? And if you think about it, the original project description said this thing should be able to drive 100 feet. Well, 100 feet would probably be pretty reasonable. The reality is, if this got caught in any of the wash from that thruster, it's probably going to get blasted out there 100 feet. That's a possibility, but that's not a part of your design constraints. So you don't have to worry about that, right? So don't.
And so, Dave, is the lander not even going to be landed before this robot ejects?
That is correct. What Glenn is, with the original objective of Jax's robot was that this thing was going to be ejected while the rocket is landing. And then
Okay.
it was going to be able to image the last,
Few
however,
minutes.
maybe seconds. It's hard to say, but we can't simulate that.
Mhm.
We're just kind of following on with the original intent of this robot
I didn't
from
modify. Yeah.
from the JAXA probe.
Okay.
But you guys are going to be in a static environment, right? We got a solid floor, we got a 6-foot drop. That's it.
Yeah.
Just stay with that.
Yeah, so Dave, it's almost as if, yeah, we're telling you, the students, this is what the original plan is, but we're taking a snapshot in time. We're not going to worry about the vehicle coming down, so we're just going to say, the point we want you to worry about is the robot coming out, landing, and taking pictures. So it's just a snapshot of that, but we're all letting you know this is what the original thing is, because as we thought about it, we realized the complexity in there, but we want something that's also measurable, that you can test, that falls within the current capabilities. And we
Right.
also, like I said, for the reference, we want to be able to find a way to evaluate all the different students and what you're doing, and this puts everyone in the same playing field, depending on how much of these items you can do and demonstrate for your robot. That helps us as reviewers determine who meets those objectives.
Yeah.
So, cool.
That's well put, Nancy. I mean,
Yeah.
it's complex enough as it is, guys. You don't need to try engineering anymore into it, right? A thought that I had was, because I kind of came up with this idea of like a little plastic kiddie pool, right? The ones I'm talking about, you can get them at Kmart or Target or whatever. You pour a little bit of sand in there, and that's your target zone. Well, at the CDR, I'm just going to line the inside of that pool with a bunch of different images. And as long as the robot can capture an image and transmit it, that's good enough. We've had questions about, okay, orientation. Once this robot lands, how will it know what direction the camera has to face in order to actually be looking at the robot? Well, that's going to require adding a lot more sensors, probably some kind of thermal sensor and an infrared sensor, and that's just adding more complexity. The just building this thing and having it land, kind of do a little lap around the target area and then take a picture, that's a lot to get accomplished in 1 year. So don't worry about anything else.
Yeah, that's well put. So do you need any help with your computer programming? Because Rochester Institute of Technology, which are very close to you guys, Michael Frank there has volunteered his students to help our Hunch students, and he actually sent out a letter about that. And if you're interested, I will send your teacher that letter to Michael Frank. Are you
Yeah, send that to me, Flo,
okay?
because
Yep.
that's a really good idea, because we had a professor help us last year on our ion engine, and that was a lot of help.
It's a big help. Yeah, good. All right, I'm sending that out because you're ready to, now that you did your design, you're ready to move on to programming.
Just to be clear, they don't have to worry about, like, it just has to go out like 6 inches from the launcher, basically, and then be able to move. That's
Correct.
We don't have to target far out.
Right, 2 or 3 feet, you'll be.
Yeah.
You don't need that.
Yeah, and
Just
the other,
not
yeah.
under it.
Yeah.
Go ahead,
The other-
Nancy.
I was going to say is for each of these projects, at the end of it, highlighted in green, Glenn has updated it and include the requirements. While it's not finalized, be sure you look at that. That tells you what we're going to be looking at to evaluate. And it says, where to position it, how far it has to drop. And that's where, when we were talking about the 30 seconds, all that's at the back. So if you follow that, and Glenn did send out an email, and I'm going to be reiterating it's my teams. That's what you guys want to follow. This is why I say you always want to go back and look at the requirements. The last page has that information, and if you're able to duplicate that, that would be great.
Yeah, thank you
And
for
meet
that.
those.
That's important. And actually, I actually copied them and sent, and this every teacher got this important information about it, and I just copied the last page of the
That's a good idea.
PowerPoints. Yeah,
Yep.
because that's real important information.
Yep.
Well, good. You did a great job. I love
Yeah,
your
nice work.
design. Yeah, that's really cool. And we'll get you in contact with the RIT professors because they could come to your school. It's so close to you.
Yeah.
All right, and if
Okay,
you
guys,
do have
nice job. Now everybody smile one time.
now everyone
Lighten
should
up.
be smiling because you did such a good job.
Yeah.
Happy Halloween! But you can
Yes.
always send a question to me. Just copy your teacher. That's important,
Yeah.
so I know. But thank you so much, and enjoy your Halloween tonight.
You
Take care,
too.
guys.
Yeah.
Thank
Okay.
you.
All right.
Bye bye. And you can stay on if you want to listen to. We got Frontier, which is also in New York, not that far
We
away.
we have club now, but I think I'm going to leave it on.
Okay.
We'll just mute and.
Yeah, sure.
Thank you.
Thank you so
Thanks,
much.
guys.
Have a
Hey,
good day.
Hey, good to see George. I think I missed you last time. So you're muted. Just want to let you know. But yeah, we're ready for you.
Hello. All right.
Hey.
So hi,
Hi.
I'm George Remay, tech teacher. Nice to meet you all. Nice to meet you, Dr. Gold.
Nice to meet you.
And these are my students. I will let them
All right.
introduce themselves.
Yep.
Um,
And
my-
I'm Nancy. Yeah, I'm Nancy Hall. I'm your mentor over here at NASA Glenn, and along with Flo. So nice to meet you guys. Go ahead.
And we have Dave Schlichting, also our Colorado mentor, who's really been a tremendous help. Thank you so much, both Nancy and Dave, for joining us. But this is another one of Nancy's schools. So Nancy is the official mentor. And they're on the other side of the state, right, than Rochester. They're a
We're in
little
Buffalo.
farther. Yeah, you're on Buffalo. Okay.
Yeah.
Okay.
All right. So I'm just going to get these guys set up because they're on my computer. So I'm just going to share the screen for their slides.
And we are recording it. Is that all right with you guys?
Yep, totally fine.
And did they do the registration?
They did.
Awesome. So it's going to be on YouTube, on the NASA Hunch YouTube.
Awesome.
I'll send Nancy the link.
All right. So we got their slides here. And so what's the process? Do you want them to just go ahead and start talking?
Well, they should introduce themselves, and then can you put your slide presentation on? Slideshow. There you go. Yeah, now it's good. But introduce yourselves too.
Hello, so I'm Adriel Rosado. I'm Dylan. So first up we had was like a rover idea where we were gonna make like a ball kind of thing, and we were gonna have like wheels in it that would be able to propel the gyros. And so
So when we were initially doing our prototyping with that, we found a gyroscope toy online that like would give us similar results to what we were thinking of. And when it would work, it would just spin in the sand and not like actually move anywhere. So we deemed it as not like a good design choice.
also, finally, for the camera part of our initial design, we were gonna have it centered in the middle, and since the ball on the outside would provide it with the rotation for it to move, the inside would be stabilized, which we determined with the other toy above. So we were just gonna have the camera stabilized in the middle with gears that would allow it to move up and down to be able to take pictures of its surroundings effectively.
Yeah, so here's a few more sketches of it. Yeah, just gotta show the video. Oh,
Oh, sad face.
this was working 30 seconds ago. Hold on.
That's Murphy's Law
Yeah.
that Dave
So
talks
well,
about.
yeah. So while he's doing that, what type of camera are you guys using?
Guys,
Oh, there it is.
There it is.
They asked what type of camera.
You know what type of camera you're using?
We're still we're still doing like exact research on it, but we were thinking of a
I was
GoPro
gonna-
system.
because
Okay.
it kind of has like the measurements of fitting into like the exact spot that we have. Because if we use like a high tech camera, it wouldn't fit.
Okay.
And we're also working on actually sending whatever it's like taking a picture of to another device.
Okay. I want to definitely give you guys kudos on taking video of it, because that's something I tell all the students as you're testing and demonstrating, do the videos, because like you just saw now, you may get to the point and have it saved someplace, and it may not work. So having that video data that we can see is good. So cool.
Yeah,
So
can you
what-
play it again? I'd
Yeah,
like to
and
see
tell
the-
us what you were testing here.
We were
kinda-
testing it in a similar sand environment that we would have to present it in.
And then we noticed that like since it's the whole thing is glass, it doesn't have any like traction whatsoever.
Okay. Oh, so what do you think you're gonna do to the glass then?
We were looking into it to see if there was any way to increase the traction of the glass, but we decided to make a new model that would completely revamp the wheels.
Okay. And is the wheels located outside or inside?
In the original model that we just showed you, the wheels were located inside of the system,
Okay.
and the glass.
But for the next prototype, the wheels are going to be outside, and they're going to be bigger than what they were on the inside.
Okay.
Yeah, I saw a little sketch of that in one of your slides.
Yes.
Yeah,
It was
'cause
on the corner.
Yeah, because this one was the one with the wheels inside, because I didn't see
Yeah.
anything. That's why I was wondering. Okay.
Yeah, there's one that, do your other slide. There's one that shows the wheels outside.
Oh,
Not that. Go one the big right there. You see in the corner? Is that?
Oh yes,
your-
is that what you're doing? The top right? Is that? No.
So we had originally, after we had determined that the glass didn't have enough traction to like grip in the sand and everything, we had thought about just adding like wheels to the side of it as just like
Yeah.
a rough idea.
Okay.
So keep the camera stable while also being able to drive around.
Yeah.
So is that your plan going forward, or is that just a sketch you were thinking?
That was
of?
just like a rough
Just a
concept we
sketch.
had.
yeah.
Okay.
Sketch.
So we have a few
Oh, neat.
other design choices that we have. So since we noticed that it didn't have enough traction to move through the sand, we decided to try with since the camera is able to stay protected, we wanted to make sure the wheels were big enough that we could house the camera in the center of them to protect them. So we determined with these wheels, or if any other materials work, we could have more traction in the sand that would allow for better movement by housing the camera in the center port.
And what's that picture on the bottom? Is that when it's all collapsed?
Yeah, so we are, because the test that we had with the actual other one, that was very recent. So this is all like really recent designs that we made. So they're not fully completed, but we are currently have two prototypes The top one is gonna have like the camera be in a small like box in the middle of two wheels, while the bottom one is gonna have the camera in like a central frame, and the wheels are gonna be slanted off to the sides,
Oh,
giving it traction to move. And for the bottom one, depending on how stable it is, we're planning to add a little wheel off the back to give it extra support when driving so it doesn't tip over and get stuck.
why did you design the wheels on a slant like that?
I was thinking that the slant might be able to like push more of the sand in the middle and hopefully try to make that into like a harder surface to allow it to get more traction instead of just slipping on the little pellets of like sand.
That's a good answer. Yeah. I was just curious.
So another reason we decided on these designs is also because since we're dropping it from a high height, we have to account that there's a possible chance that it might flip over. So if it's like all centered on one end, if it flips over, it'll just land on its head and we'll be able to move around it all. So we had to design it so that it would be able to flip 180 degrees.
So, quick question: have you guys done any preliminary calculations to see the weight of the stuff you have so far?
We have had some rough weight at the printer,
Right.
and so far the weight is within its range. It's varying a lot in the designs, but they're going to be within the range so far.
Okay, that's good. I was just asking because I didn't see anything, and that's something good just to check and at least see where things are going. All right, very good.
All right, this is your.
What are the dimensions of these two robots?
I'm pretty sure the top one had the wheels at 5 inches.
Yeah, 5 inches.
And the bottom one I think was 4.5 inches the entire wheel. And for width, it was this was built in millimeters, the bottom one. So the like entire width of it was 50 millimeters, which I'm pretty sure fits in the dimensions.
Then the length of the top one is 4 inches.
Okay. Very good. So what kind of motors are you using to power the wheels?
So the top one, I was thinking of we're waiting on the order, but we have a dual-sided DC motor, so it can control both wheels.
Oh, okay.
And yeah, the bottom one was also going to receive that as well.
Now, if you have one motor, how are you going to get this thing to be able to turn?
So my idea for the top one was that since it's dual-sided, we could control one side where it turns the wheel and keeps the other one, so it'll spin.
Okay, like, dual-sided meaning you do have two different drive axes, right?
Yes, it's a split.
Okay. It's a split.
Makes sense. Yeah, thank you. Okay.
Any other questions on this slide specifically?
No, that's good.
So our idea on propulsion was kind of shooting for like kind of like the way of a gun in a way. So like using like Nerf gun specifically. Being that like we're gonna use like a sort of like a spring in the back as like the piston. And like as it's drawn back, it's gonna like have like a rearward position by a catch. Whereas when that catch is like in like its middle position, it's gonna be released. And then when the spring kind of like from the back lurches up, it's gonna like push the wall because we're gonna have like a wall that pushes out the robot, and then we're gonna utilize like as air, kind of like push it back. And then kind of use like the same way as a Nerf gun works, but like in a slower like way, because when it like makes it go like faster, but not as fast.
So how big is this mechanism going to be?
As of now, it's kind of gonna be like the width of the in between like where the camera is, like in the box part. It's gonna be about right there, and then it's just gonna push it. I don't have to.
So this is integrated into the robot itself.
No,
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 this
no,
is gonna
no.
be
No,
No.
it's just mounted on the inside of
Yeah,
the
it's
box.
gonna be mounted on. It's not gonna be like inserted anyway. It's just gonna be able to push it out.
Okay, so this is
Okay.
for the ejection device.
Yeah.
Yes.
Okay.
Okay.
And I just want to clarify this, maybe Dave or Nancy. The robot has a 15-ounce limit on it
Yes.
for weight, but this does not count.
Correct.
That,
Yes,
as long as it's not in the robot, it doesn't
But
add
Yes,
it
it
doesn't
is
count.
not.
Doesn't
It's
count.
not gonna be in the robot.
Yeah,
Yeah.
I've had several students ask that, and we're like, the ejection system does not count.
Count.
Correct. Yep.
Right.
Okay.
Nope.
Okay, good.
So there's not
we-
like there's not a specific weight limit for this device.
No.
Okay.
No, but again, let me offer you an even more simplistic idea here, because I think you're on to the right idea of using a spring. If you had just a coiled spring secured to the back wall of your box, and you put your robot in and compress that spring and then close the door on the front of the box, the spring is loaded.
Mm-hmm.
Right? As soon as you open that door, it's going to push that robot out.
Yep.
Now, what you will be allowed to do, because again, coming up with a mechanism that would open that door of the box is even more complex. You can imagine that the door has some kind of a hinge on it, right?
Yes.
Whether it opens up or down is somewhat irrelevant. The whole point is when it's down, you have some kind of a little pin or a latch that keeps the door secure.
Yes.
Now at the CDR, you can take your box, put it on top of the 6-foot stand, and then someone will be allowed to grab that pin and pull it.
Mm-hmm.
You can do that to simulate what some future iteration would involve a more mechanical system.
Mm.
But the whole point being is you pull that pin, you've already got a preloaded spring in the back. That door, it's just going to push it right out.
Yeah.
That it doesn't have to get any more complex than that. You just have to know that your spring has enough force for this robot to clear the box. And then then gravity takes effect, right?
Yeah, that's kind of like the reason why I went with a spring rather than like having like a complicated piston.
Yeah.
That's why I chose a spring.
Exactly right. I'm encouraging everybody to keep it simple.
Yeah.
Right.
Okay.
I'm just worried that they're going to open that door and the robot's going to go way further than the 3-foot diameter.
Well, that's where your testing comes in.
Yes.
Right. So you need to test that.
Depending
spring.
upon the mass of your robot, you're going to have to have the right size spring with just enough force for that robot to clear the box.
Mm-hmm.
Right.
Okay.
Doesn't have to be 24 inches or 36 inches. Clear
Nope.
the box, which it did say. Just clear the box and
Yes.
and stay in the little waiting pool.
Mm-hmm.
Correct. Okay.
Are there any more questions?
Anything else, guys?
Yeah. We have a few questions. With our two designs that we have, which one do you think could possibly be more effective?
Of these.
Well, the go-to answer from any mentor is going to be testing is going to tell you what that is.
Yeah. Yes. And the other thing,
Go ahead, Nancy.
I was gonna say the other thing is look at what the requirements say, see which design meets the requirement the best, and then testing. It's okay at this point to have two designs, but your testing is what's going to determine it. That may help you out, and also go back to the requirements. And in this case, at the back, look at the items in green. Is there one of these robots that does a better job of meeting what you need to demonstrate?
Right.
Mhm.
Right.
And it looked like you already had a little sand pool. right? Did you already test that round robot?
We did not test this one yet.
No, but that plastic ball, you had some kind
Yes.
of
Yes, it was just
a container of sand, so you've got something to test in.
Yeah, you got
You
something
know,
to test.
the other thing I would say is keep it simple, right? Realistically, the image on the top is pretty simple, right? There's not a lot in that. One thing I might suggest in that top image, if this thing comes out and has a tendency to kind of roll it all, it may land on the side, on the edge of one of those wheels. And you may have a hard time uprighting it at that point. But if you were to create a semi-sphere on the outside, kind of a hub on those wheels, so if it landed, it's going to have a tendency to want to roll over and right itself. Did that make sense? I didn't do a very good job of explaining that. But again, I think that either one of those has good potential to it. They're both pretty basic. So I would mock them up. You don't even necessarily even have to print all this stuff out, guys. You could manufacture some of this stuff in cardboard or balsa wood and just do some very simple testing.
Yeah. No, that's great advice.
And then, so like when it came to propulsion, what like, I guess like sort of like big factors would like affect like the efficiency, like for say like the spring.
Yeah, that's again, I think that's all going to be just you're going to get some springs and test them.
Yeah.
Okay.
See how far a spring shoots one of these things.
Okay.
Yeah, as long as you've got equivalent masses, it should give you some pretty simple results. And again, the thing that I've been commenting to the other teams, have you guys already purchased all your electronics? Do you have the board you want and the camera and motors, etc.? So you know what the mass of all that is, right?
Yes.
What I would do is build the shell of your robot and don't even put your electronics in it yet, because you need to do some drop testing. You want to make sure that your design is robust enough to withstand the impact of that 6-foot drop. And it's better to do that without expensive electronics inside. Okay. All right.
All right. So the last two questions are kind of been already answered with the testing one, like the testing thing. But I have another question about these two designs right here. Would the curved thing at the bottom provide like any extra benefit, or would that be just proven by testing?
You're going to have to test that.
Right.
Maybe test it both ways with the angle, turn the thing upside down and test the other side of it. It doesn't have an angle, and see which one works the best.
The one thing about either of those designs is if it comes out of the thing and kind of lists one way and lands on the side of either one of those, it's got to have a way to upright itself, or you're kind of dead in the water.
Would we be sorry?
So just add some curvature on the outside of that, so that if it does come down on the side, it's going to have a tendency to roll over one way or the other. Okay.
Would we be allowed to, like, since we have that size limitation of it inside of the spacecraft that's going to be bringing it there, would we be able to have, like, I don't know, maybe arms on the side of the wheel that are like spring loaded to where once it clears it, it's able to shoot out like these two arms that once it lands, it's able to keep it stable and not completely fall over. Like if it tilts too far, one of the arms will catch it.
You could do that.
Sure. Yeah, so that would be part of your design. So yeah, if you want to design it that way.
It definitely can expand after it leaves that box.
You bet.
That's true.
Okay.
So that might be an interesting way to solve the problem of it not landing in the right orientation. Any other questions?
I think we're all set.
Okay.
Awesome.
Okay, well, nice
Nice.
design and nice work.
Nice presentation, guys. Thank you
Yes.
very
Yep.
much.
Yep. Thank you for your work on that.
Yep.
Dave, so I'm more than willing to help you with any of your PDRs because you've been such a great help. You mentioned you had another one today, or was that not a
this
PDR?
this is just a follow up with one of my teams. They're
You
doing
already
some
did
work.
your
Yeah,
PDRs.
and actually, I've got quite a few teams that Allie's considering for the HR conference in January. So obviously, those students are working feverishly right now. They have until December 5th to make their final pitch. So they're all vying for time to every little design modification. But that's
Yeah.
Yeah.
So is
Okay.
that it?
Well, I have.
Is this the last team?
Yeah, so
for
yeah,
right,
so
for
the
right
other
now.
students, yeah, so are we done with the students? Because I have a question for you guys if they want to go. You guys
Well-
have any questions for us or?
Nope.
You good?
All right.